We continue with our series of finding the electric field due to various charge distributions. This time we have a semicircular ring of charge, and it has a radius that's given as 2r, and this is just a point right here in the center, and we want to know about the electric field right there. So at that point, let's draw dE, dEx, and dy vectors that are due to this dq element shown. So dE would point in that direction right there. dq is positive, so the electric field should point away from it. Well, in terms of horizontal and vertical, there's a dEx right there, and then there's a dEy that's right there. So I could break that dE vector into x and y components, write another theta in the correct place based on what we've shown here. Well, if this is theta, then this here is theta right there. Give a qualitative description of the electric field at point P. That would be that it points straight upward. All of the horizontal, or what I've called the x-axis, all of those are going to cancel each other, because isn't there going to be another dq right here where I'm pointing, the x component of which is exactly going to cancel the x component of this dq. So all the x components cancel, and we only have a net dEy from each of the little dq's around this semicircle. Let's write an expression for the differential component of the electric field that will not be canceled out. In other words, dEy. What is that? Well, let me redraw what we had here. There's dE right there. dEx is right there. All of those end up canceling. So what we're really interested in is this dEy right here, and then there's a little theta right there. So what's dEy? Well, it's equal to dE times the, what would this be, sine of theta. dE is k dq over the distance squared. The distance away is 2r, so 2r squared is 4r squared. That would give us dE, but we don't want dE, we want dEy, so we need to multiply by the sine of theta. Now, let's add whatever is necessary to this figure to show and label the differential angle d theta. What we need to do is d theta is a tiny little angle right in here. I'll show it in the middle, but show it wherever you want. That little angle right there is a tiny little angle that exists right in there. So there's d theta. What proportion will help us get dq in terms of d theta? One more time, d theta is right there. And what's the ratio? Since this is a uniform rod, dq is to d theta as q is to pi. That little amount of charge compared to this little angle is the same as this total amount of charge compared to this angle, which is, as we know, pi. What we can do then is we can say dEy was k dq. I'm recopying my work from the previous page here. dq, if we look at this ratio, dq is going to be q over pi times d theta. So let's put all that in here. Q over pi times d theta. You check and make sure that I've got all of that in the right spot. In place of this dq, I've put q over pi, and then I put a d theta in there. And so now what we're going to do, isn't it true? We want to integrate all of this to get our total EY. And we're going to integrate, you can see, from theta equals 0 to theta equals pi. So what do we get here? Everything here is a constant except for the sine theta d theta. So here's the next step on the path. kq over 4 pi r squared. When we integrate sine theta, we get the opposite of cosine theta. And we need to take those limits from theta equals 0 to theta equals pi. So where does that leave us? kq over 4 pi r squared. Then cosine of pi is -1. So that is the opposite of -1. And then we go minus the opposite of cosine of 0. Cosine of 0 is 1. So what is that? That's +1 and +1, that's 2. Which means we need a 2 in the numerator, which I think would cancel kind of like that. And there you go. That's the magnitude of the electric field right at that point in the figure, and that electric field is directed straight up to the top of the page.